Hello everyone. Welcome to one more session of live discussion with Suresh Dwivedi and Ashwini Kumar Sinha. Today our topic of discussion is hyperspectral sensor. So my first question is what is hyperspectral sensor and where it is used?
Yeah, so basically, you have seen the light spectrum. So there are the electromagnetic waves, and in the electromagnetic wave, there are lots of wavelengths are there. Some are visible length, what we call the light, and some are invisible, like infrared or similar to that, infrared, UV ray, or there are different other wavelengths are also there. So all of these are called spectrum, different wavelength of light. All of these called a spectrum. So the hyperspectral sensor, with the name of this, you can find it's a sensor that can sense the spectrum of light, the light, visible light or non-visible light like infrared or near the NIR, near infrared, or the UV light spectrum as well. So these sensors are generally used for getting the colors, getting the wavelength measurements from the reflective surface of the light source. Okay, so these are generally being used in the remote sensing, where you need to sense remote sensing of this, or doing the SWAN analysis, or the finding the compositions of the milk, something like that, or it can also be used in geology and mining for identifying the minerals of using the spectrogram, or you call spectral analysis, using the spectral analysis methods. And this can also be used in medical sensings for sensing different kind of tissues, nerves, and disease. Okay, and it can also be used in the food safety. And so these sensors are widely used in many areas for the color analysis and spectral analysis. Like in the phone displays, you have seen the every display. If you get the one display of one phone and another display of the another company phone, and when you run the same video, you might have noticed the both videos colors are very little bit of different, and so in some cases they are very different. Like what's showing in my one phone color is red, some phone color shows that other shades of red. So there is a difference between the both red colors. Both are the same video, both are the same format, both are the same setting, but the displays are showing different shades of red color. They both, even though the videos are same, you might notice with the TV, laptops, or phone display. So these as hyperspectral sensor also used in these areas for the color correction, to correct the colors of these displays. Okay, and then the another huge cases of these hyperspectral sensors are uh, you have seen the packaging of very different packets. Okay, like suppose a Coca-Cola, they have the red color with the white color written on it. So in some case there might be happen that due to little bit of color constituent difference in the material, it might be some more red, some are less red. Also all the packaging of the all the consecutive bottle might vary with the one bottle. They need to make it look similar. So there also be need for the color correction in these area, in packaging area areas. So it's in display for the color correction, in the packaging for the color correction, in the spectral analysis we are using it for the using this spectral hyperspectral sensor spectral analysis to find the disease and curing the and also in the medical fields for the medicines as well. Environment monitoring, like it can detect the pollution, the water quality using the spectral analysis with the reflectability of different wavelength lights in that. It can also be used in finding the minerals of minerals on the another planet. Okay, so the light coming from those planet, okay, when passed through the prism, they create a that single light, that white light get transversed and when passed through the prism, and then they convert into the all the seven colors. But depending on the constituent and the environment of the other planets, okay, the certain wavelengths of light got absorbed. Like if there is a more number of nitrogen in some environment, or more number of oxygen in some environment, some more number of HCl, hydrochloric acid, in some environment. So based on those constituent of environment on that particular planet, and when the light reflected from that planet, according to those constituent, uh, the color, some color wavelength get either absorbed, or either get more reflected. And based on that wavelength, when you observe from the telescope and pass it through the prism, and got the constituent wavelength of that white light, passing through the prism, and then using the spectral analysis, you can estimate what is the presence, what kind of mineral present in other planet also. So we can also use in this astronomy as well. So it's a very wide area of use.
Sorry. Okay. What are the key design considerations when developing a hyperspectral sensor? Should I repeat the question?
Yeah, yeah.
What are the key design considerations when developing a hyperspectral sensor?
So spectral sensor range and resolution is one of the most important factor, like defining the wavelength and the range of which you are trying to capture, which you are trying to get, like the range of 400 to 2500 nanometers of the wavelength. Okay, the number of spectral band that you want to measure, the red light, violet light, near infrared light, NIR. And there is one more use of this hyperspectral sensor is the flickering. You might see a flickering of light and all those things. So it can be calculated used for calculating that as well. And then there that is similar to noise ratio, the size and weight of the power, size, weight, and the power consideration. So all are different things that you need to consider while selecting and designing the hyperspectral sensor. So one of the most among all these things, most important is the resolution and the wavelength that you are going to capture, that you want to capture, that you want to gather data about.
Okay, so, how do you select the appropriate detector array and optical components for a hyperspectral sensor?
Yeah. For selecting the appropriate detector array and the optical components for the hyperspectrum sensor involves aligning the system's capabilities with the intended application, spectral range, and the resolution requirements. First, consider the spectrum range and the resolution. It defines the spectral range of the interest, typically VNIR 400 to 1000 nm, SWIR 1000 to 2500 nm, or beyond. The detector material must match the range. For VNIR, silicon, CCD, or CMOS sensors are common. For SWIR, in, uh, in gallium AS arrays are preferred. Resolution requirements will dictate the detector's pixel size and the count. Next is the sensitivity and the noise. The detector spectrum have high quantum efficiency in the target spectrum region and low dark current noise. This ensures a strong signal detection even in the low light condition or with the narrow spectral band. Another topic is the optic compatibility. Optical components such as lens, gratings, and other filters must be capable of with the spectrum range and the spatial resolution. The optics must minimize the abbreviation and the transmission losses. So, materials like fused silica or sapphire are used for the broadband transparency. Grading should be chosen based on the dispersion characteristics that suits the desired spectrum resolution. Another parameter which we have to consider is the field of view and the imaging mode. consider the application's spectral requirement. Push broom system need linear detector arrays, while the snapshot system use 2D arrays. The optical system must support the desired field of the view without introducing the distortions. Next parameter is the environmental and the system constraint. Temperature, stability, size, weight, and the power consumption influence the choice of the component, especially for the airborne or the satellite platform. Ruggedized components may be needed for the harsh environment. So in brief, we can say that component selection balances spectral performance, imaging requirement, and the operational condition. System modeling and the simulation tools are often used to optimize this configuration before prototyping.
Okay, so what trade-offs do you encounter between spectral resolution, spatial resolution, and signal-to-noise ratio during a sensor design?
Yeah, so trade-offs between the spectral resolution and spectral resolution and SNR each that a spectral resolution, let's first compare between the spectral resolution versus spectral resolution. Okay. So higher the spectral resolution means the narrow that means in narrower bands. Okay. So require more detectors of pixels to filter and to get to capture the more lightning per band and potentially lowering the SNR. Okay. So if you want to get more spectral resolution, then you will get less spectral resolution. Okay. If you want to get more spectral resolution, then you will get less spectral resolution. Okay. So this is one of the things. Then the spectral resolution versus SNR. Let's talk about this. Okay. So the narrower the spectral bands collect less, as you narrow the spectral bands, okay, then it collects a less number of light because the bands are narrow. Okay. So they collect a less number of light. Then if the less number of light get connected, then it reduces the SNR, especially for the low light conditions. Okay. So this is another thing. And then let's go for the spectral resolution versus SNR. Okay. So the smaller the pixels captures, okay, smaller the, if the spectral sensor pixels are smaller, that to capture the light. Okay. So it captures the less light because the pixels are the smaller. Okay. So it's again lower the SNR. Okay. Where, while the larger pixel, it will increase the SNR. Okay. So this is the another point and the trade-offs of this.
Explain the difference in designing push broom versus whisk broom hyperspectral sensors. How these how do these design choice impact complexity and data acquisition?
Yeah. Designing push broom and the whisk broom hyperspectrum sensors involve distinct approaches, each with the implication for the system complexity and the data acquisition. First, consider the bush broom sensors. Actually, bush broom systems use a linear detector array to capture one spatial line of the scene at the time as the platform, for example, satellite or the aircraft. Moves forward, successive lines are acquired, building a 2D spatial image with the spectral information at each pixel. These systems require precise stabilization and alignment to ensure the scan lines from a coherent image. They benefit from high sensitivity, fewer moving parts, and the faster data collection, making them ideal for the high resolution, wide area imaging. While in case of the whisk brown sensor, in whisk brown sensors, use a single point or a small linear detector that scans the essence pixel by pixel using a mechanical mirror or a rotating system, which this sensor sweeps across track to build one image line while perform motion provides the along track dimensions. This setup often allows for the higher spectrum fidelity due to the consistent light path geometry, but comes at the cost of increased mechanical complexity and the slower acquisition rates. When we consider about its design impact, so in case of bush broom systems are typically less complex mechanical, but they require more sophisticated calibration and the motion compensations. They generate large volume of the data quickly and are better suitable for the real time or the near real time applications. In the contrast, whisk broom systems are mechanically complex due to moving parts but can offer better control over scan uniformity and are more adaptable to varying scenes geometries. However, their data acquisition is slower and often less efficient for the large area coverage. When we summarize, we can say that the push broom sensor favor speed and the simplicity, ideal for the wide area and the movable platforms, while whisk broom designs offer precision and the flexibility, but at the cost of mechanical and the operational complexity.
Okay, so how do you approach thermal management and calibration in hyperspectral sensor hardware design?
Yeah, so in terms of hardware designing, especially if you talk about the ultraviolet range of a spectral sensor or spectral analysis, or the infrared based range of a spectral sensor, spectral analysis, or NIR, near infrared range. Okay, all of these, especially for these, it also applicable for the other as well, but especially for these infrared and the near infrared or the ultraviolet UV range of the spectral analysis detector, they generate a lots of heat because these light waves carry lots of heat. With the infrared is very, carries a lots of heat itself. It's heat up the element very hard. Okay, with that and with the while the fluctuation of the temperatures, there might be the misalignment in the optic, and or you see the shift of a spectral response. So if you want to have a solution for this kind of thermal, and you want to manage the thermal and do the calibration according to the thermal errors, or the thermal or the change of optics behavior due to the thermal fluctuations, then one you can use is the active cooling, like the pad heater, or you call what we call the, its actual name is the thermoelectric cooler. Okay, what we call the Peltier or Peltier, whatever you pronounce. Okay, so use this kind of active cooling things for the infrared detectors to maintain the low noise and maintain the thermal, do the thermal management. So basically, these thermoelectric TEC, sometimes we call it TEC, sometimes we call the same device TEG. So here, what happens? These thermoelectric coolers are also thermoelectric generators, or so it can either cool down, it can either generate the heat as well. So one side it make cool, it's do the energy transmission. Okay, transmit one side of energy to the another. So same way like your AC do the, it transfer it. How do it put it? Transfer your room heat to the environment. Okay, outdoor environment. So it do only one thing, the transferring of heat. So it can either transfer the heat from the cooler area to, to make it more heat, room more heat, or even transfer the heat from your room to outside to make it more cool. So it can also be used as a generator. Okay, so but here we are talking about the TEC, that is where we are using that thing is it TEC, thermoelectric cooler. Okay, so you can use this device for the thermal management. This cools the sensor. Okay, so yeah, this is or other you thing you can do is the, spectral calibration. So you can use the various calibration methods and algorithm to analyze the errors and recalibrate the sensor readings as per the thermal errors caused by the thermal errors, using the feedback loop, and then it correct the errors, like this is thermal, this is error due to this thermal this range of thermal uh, you know mm, uh, thermal shift in the optics, then you have to give the feedback, and then it correct the error, then you it again run in the feedback. So it's a feedback loop. Okay, so you can do the calibration as well, or you can use the thermoelectric coolers as well.
Okay, so what considerations go into the choice of material and coating for optical elements and hyperspectral sensors?
Yeah, what consideration to go into the okay, yeah. uh so if we talk about these considerations, there are it depends on the use cases. Okay, so where you are going to use and how you are going to use, if you want to measure the measure the wavelengths around the UV rays, or long wavelength length, like or in infrared range. So it's depend on you, on your use cases, on which area we are going to use, and you have to choose the material according to that. Okay, so if you are going to the if your spectral sensor range is between the 400 to 205 nanometer, then you can use the fused silica, that it is excellent for the UV or near infrared, that is the 200 to 2200 nanometer, due to the high transparency and very high dispersion. Okay, you might have seen the dispersion of light, you have heard about that. So that can help in that, due to the very low dispersion rate and very high transparency, fused silica can be used. The another one material is the calcium fluorocarbide, CaF2. Okay, okay, so calcium uh, fluoride. Okay, so CaF2. Okay, so this is used for the another UV, that is the ultraviolet range. Okay, or mid infrared range, that is 180 nanometer to 1000 to 8, sorry, 180 nanometer to 8000 nanometers. Okay, because this can help you if, with the no, low colorimetric abbreviation. Okay, so then for the thermal stability, you can use the material like that has a low thermal coefficient. Okay, and for the mechanical durability, all your optics must have to be to stand with the vibrations, the shocks, the another that we have already talked about, the thermal and can able to handle those thermal optic shifts due to the thermal. Okay, low, so you low optic shift due to the thermal expansion, or thermal effect. Okay, then you have to you can use you have to select the material accordingly. Then there is a mechanical durability that I have told you about earlier, that vibration and the shocks. Then the reflective index and dispersion. Okay, so selected material with appropriate reflective index to minimize the chromatic aberration across the spectral range. And then the low dispersion materials like CaF2, like we have told you earlier, are profound for broadband application and maintain the focus across the wavelengths. Okay, and there are different other considerations that you have to take, like the cost and the manufacturability. Okay, and there are some coatings for the optical elements, like the anti-reflective AR coatings. So like even in the TVs, in this kind of LCD TV, you have seen there are different LCD materials or layers out there that reflect the less light coming from the top side. Okay, so it's make you give more clear image. So same goes for the spectral sensor as well. There are anti-reflecting coatings are paints are there. Okay, so minimize the reflection of the transmitted waves. Okay, or you can do the multi-layer coating software. Then you can add the band pass filters and different other filters as well. And okay, and for the environmental factors, you want to you want to protect it from the moisture, dust, and very high radiation, then you can use the protective coating as well. So there are different considerations you can take in while selecting the materials. And okay, so all of these are the considerations that you can take. Okay.
Okay, so how do you design the electronics and data acquisition system to handle the high data rates generated by hyperspectral sensors?
Yeah. Actually, designing electronics and data acquisition system for hyper spectrum sensors requires careful consideration to manage the high data rates generated across the numerous spectral bands. The key is to create a streamlined, throughput, high throughout system that can efficiently capture, process, and store or transmit large volume of data in the real time. When considering about the high speed analog front end, AFE, electronics are essential for the accurately capturing the analog signal from the detector. These are the paired with the high resolution, high speed analog to digital converter ADCs to digitalize the signal with the minimum latency. ADCs must be selected to match the sensor's frame rate and the spectral resolution, ensuring no data loss during the acquisitions. To handle the resolution data rates, field programmable gate arrays FPGAs are often used as the primary processing units. FPGAs offers parallel processing capabilities, enabling real-time data handling, initial pre-processing, normally, for example, calibration, correction, etc., and the compression. This reduces the data losses, data volume before it reaches storage or the transmission modules. So, and that is the efficient data buses and the memory architecture, such as DDR4 or 5, RAM, and the high-speed serial interfaces, for example, PCIe, LVDCs, are implied to sustain the required bandwidth. The system must be architected to avoid the bottleneck between the sensor, processor, and the storage transmission. Onboard storage solution is also very important. For example, high capacity, non-volatile flash memory are used when real-time downlink is the impractical, where the possible lossless or the near lossless compression algorithms are the implemented to reduce the file sizes without compromising spectrum integrity. So, power and the thermal constraints are also addressed during the electronics design. Low power, high efficiency components are the prioritized, and the thermal management is the integrated via the heat sink or the conduction path to avoid the performance equation. So, a successful data acquisition system for the hyperspectrum sensors relies on high-speed ADCs, FPCAs based processing, efficient memory, and the data path, and the robust components that ensures reliability, real-time operation without tight SWAP constraints. So,
Okay, and how would you test and validate a hyperspectral sensor prototype before deployment? Should I repeat the question?
yeah.
Okay, so how would you test and validate a hyperspectral sensor prototype before deployment?
Yeah. Hi. Actually, you will reply this one.
Yeah. Okay. I will take this question here. So for testing and validating the hyperspectral sensor or prototyping before the deployment, uh, there are various testing process of validations before the deployment. That one is the spectral calibration and accuracy testing. So how accurate your spectral sensor is for the particular range of wavelength. Like if you want to verify the accuracy or map of wavelength to the detector pixels across the spectral range like 400 to 2500 nanometer. Then you can use the monochromatic light. Monochromatic light, any might have, if you don't know what is the monochromatic light, let me tell you. If these are the light that you see here in my room, okay, these lights are spreading across the different axis, x, y, z axis in the all directions. Okay, so this is not the monochromatic light. Okay, and with the different colors. Okay, so what is monochromatic light? So if you have lead this in the standard 12, or even in during the engineering, the monochromatic light or the polarized light, and all those things. So monochromatic light is the, like here in this white light, you can see if I pass this through the prism, okay, you can see the different colors, wavelength of the light out there. So we need, when it comes with the monochromatic, so you can get the little bit of idea about mono means one, and chromatic. Okay, so mono, one thing you got is the one. Okay, so monochromatic light is a single wavelength light. Okay, so like either the 532 nanometers green laser light, or some other particular wavelength of light. So monochromatic light, the light rays that consist of one wavelength. Okay, that is the monochromatic light. Okay, now this part you understand. Okay, now go for the earlier question that we have. Okay, sorry for getting from here to there, but to make you understand this, I have to make you understand what the monochromatic light is. Okay, so if you if for the spectral calibration and accuracy testing, suppose that we want to verify the spectral sensor that maps the wavelength to detect the pixel across the spectral range of 400 to 2500 nanometer. So one method is to use the monochromatic light source like the tubular laser or the mercury argon lamp to illuminate the sensor with known wavelength. Because okay, so these spectral sensors, what these do they measure the different shades of the light, the different wavelengths, the shades of the light, different shades of the light means different colors, and different colors mean the different wavelength. Okay, so if you're using the monochromatic light, so earlier I have told you that what the monochromatic light is. Monochromatic light, one single wavelength. So here your wavelength is known. Okay, you know the wavelength of that particular light, particular shades of light. Okay, like green, red, or blue, whatever the shades, that particular shades, you already know the particular wave, that this particular light source is illuminated this wavelength, that is the 400 nanometer or 2500 nanometer, whatever the range it. Okay, because your wavelength source is known, the shades of exact shades of the light is known. So you can use the spectral reading. Now what the spectral reading is giving you, what is the wavelength of the light that is being detected by the sensors. So if there is a difference between the one source light that your wavelength is already known, and if there is a difference between, then you can find the error between, and then you can recalibrate it, or you can analyze this spectral sensor not working because it's showing the some different wavelength of light, while my known wavelength range is this. It is eliminating the wavelength in this range. Okay, so that is one of the tools that you can do. Or another is the radiometric calibrations. So our sensitivity test. So to ensure the accurate measurement of light intensity across the all bands, and SNR, we have told you, that adequate signal to noise ratio. Okay, so for this, you can use the method of calibration by integrating the black body source to provide the uniform and radiance levels. Okay, so there is a black body source. It means what I can say, you can put the sensor to black box, and then you can put the spectral sensor over that, and then try to measure the what's the reading of that spectral sensor in that case. Okay, so this is another thing. Then the spectral resolution and image quality testing. Okay, so to confirm the sensor ability to resolve the spectral details and produce the distortion free images, you can use this. The method can be used that image standardization patterns that USAFE 1951 resolution target to measure the spectral resolution and modern transfer function, MTF. Okay, You can use the tools like resolution targets or collimated light sources or image analysis software can be used for that. Then you can use the Strelite and crosstalk testing. Okay, so all of these there are. Then the another testing you can do is the environmental testing. So or what in environmental temperatures, humidity, vibration, radiation, how these spectral sensors are performing. Okay, and what are the optic shifts are due to these environmental factor. You can try to test with different scenarios. Okay, so these are the things that you have to test. You have to test and to validate the hyperspectral sensor before the deployment. And after getting this result, you can if the result is according to your meet, then you can deploy it. Otherwise, you have to go for the again loop. Feedback loop, feedback correction, then recheck, feedback correction, the ones what we call the rule of evolution, where you evolve the product and your deployment, fixing the error again and again and getting the feedback again and again according to the test. Okay.
Okay, so what are the design challenges related to hyperspectral integration with other systems?
Yeah, just actually integrating a hyperspectrum sensor with the system like GPS, uh, inertial measurement units, IMUs, and the onboard processors presents several design challenges, primarily related to the synchronization, data fusion, and the SWAP size, weight, and the power constraints. First, discuss about the time synchronization and data alignment. Actually, precise geo-referencing of the hyperspectrum data requires tight synchronization between the sensor, GPS, and the IMUs. Any timing discrepancies can lead to spatial misalignment, especially when the mounted on the first moving platforms like UAVs or satellite. This is a very necessary and highly accurate time stamping and the coordination across all the systems using protocols like pulse per second PPS and the real-time clocks. And that is the mechanical and the electrical integration. Physically integrating multiple subsystems into a compact form factor demands meticulous mechanical design, vibration isolation, thermal management, and the electromagnetic shielding must be addressed to avoid the cross interference and the performance degradation. Electrical performance must support high data throughout while maintaining the signal and integrity. Another parameter which we have to consider is the power management. It is also very important. Integrating multiple high performance systems within a limited power envelope is a significant challenge. Efficient power distributes low noise power supplies and the smart power management are the essential to avoid the performance loss or the thermal overloads. So power design, power supplies is very important. Next parameter which we have to consider is the data throughput and the processing. Hyperspectrum sensors generates large volume of the data. So, integrating onboard processor capabilities of handling real-time processing, data fusion with GPS or IMU inputs, and the compression requires optimized software and the hardware co-design. So, memory, bandwidth, and the processor speed must match the sensor's data rate without introducing latency are the bottlenecks. Next parameter which we have to consider is the software integration and the calibration. Ensuring compatibility across the different system of the software sensor driver, and the calibration routines is complex. So accurate sensor fusion algorithm are the required to integrate spatial GPS REMU and the spectral data streams. Often requires extensive testing and the calibration under the varying operational conditions. When we summarize these things, so we can say that the successful integration hinges on precise timing, robust mechanical and the electrical design, efficient data handling, and the harmonized software. All are the operating with uh, stringent SWAP constraints. Yes.
Okay, so what strategies do you use to optimize power consumption in hyperspectral sensors intended for remote and airborne platforms?
Yeah, you can use the different strategy for the power consumption in the hyperspectral sensor when you want to use to deploy in the remote areas. One is part of the communications part, and another is part for the for the range at which you are going to measure it. Okay. So suppose that if you are going to get the spectral, you want to do the spectral analysis at the time interval, you not need to be used that spectral sensor for that long period of time, like not continuously. You want to gather the data around the day, then the midnight, and then then the evening. Then not need to turn on the whole sensors for all those times. You can turn it off. So you can add the sleep function in the sensors or the device that you're using there, where you can put on the or turn on and off the sensors based on the time intervals that where you want when you want to use it. Okay. And the second thing is you can add the energy harvesting modules out there. There are PMICs integrated with the sensor IC. Okay, so PMIC is the power management IC, and there are a lot of energy harvesting ICs. One is from the EPH that you might have seen in the electronics for two innovative sections we have selected earlier. So these in PMICs use the light energies or vibration energy or environmental energy and all the ambient energy sources to harvest the energy and then use this energy to drive the sensors or to charge the battery and so it can overall it optimize our overall power consumption, because these energies are being used from the environment to power the sensor module for transmission of the data to the remote areas. And second is the already I've told you that regarding the you can optimize the power using the sleep modes and making the persons in the sleep. Okay. And then the another thing, you can use the different type of technology for the remote data transfer of these spectral sensors like BLE, LoRaWAN, or you go Wi-Fi, Zigbee, based on the different power consumption. So support there you now need to transfer between the shorter range, or if you're doing it in a mesh network, then you can use the BLE. They can use very low amount of power, so you can combine with the sensors to transfer the data and the remote analysis of the spectral analysis. Okay, you can use the Wi-Fi with the sleep mode, deep sleep mode, light sleep modes, Wi-Fi modules. So you have lots of ways to do that.
Okay, so my last question for the session, what are new developments in hyperspectral sensor and its use cases in future?
Yeah, so there are lots of new developments are happening, and the use of these hyperspectral sensors to make the more new and advanced technologies using these hyperspectral sensors. One I've told you that it can be used in the cosmic exploration and the planetary analysis. How what are the constituent of the materials, minerals, or kind of environment in the remote planet galaxies using the spectral analysis, because of the reflectability and the absorbability of the light based on the environment on the different planets. Okay. And we are using this earlier as well. We are using this for the decades. This is how we able to know that what are the environmental condition on the Mars, what are the environmental condition on the moons, what are the minerals available on the Mars, what are the minerals available on the moons by using this spectral analysis. Okay. Second thing, we are using we can be use these for detecting different kind of disease, cancers, and different kind of disease. There are lots of research happening there. Then one of the most interesting things recently happening, that many companies are claiming that they have already succeeded in this. Some are working, are still working in in this. So some have completed the research, some are making the product around it. So that is the glucose analysis of the in your blood. So like in all the traditional method of the glucose analysis or sugar diabetic patient, sugar measurement for the diabetic patient is the pricking method. You prick the needles to measure the sugar. We need the blood for that. But here we can use the many research are going on there, that we can use this spectral analysis and do the spectral analysis of the blood, and based on the light absorbed or reflected due to those glucose or sugar molecule inside your blood, you can estimate the amount of sugar present in your blood. I can do the real time sugar monitoring and sugar analysis thing. So there are many companies out there claiming that they have already developed a device with non-invasive sugar monitoring device that work on the spectral sensor. There are few companies who claim to be working and already have completed their prototyping. So there are lots of research that happening around these things.
Okay, Suresh, so do you want to add something to this?
No, I'm not interested to add something. It is sufficient.
Okay. Okay, so this brings us to the end of this session. If you have any question, you can post in the comment section. Thank you for your time.
Thank you.